Let's try some word association. I'll say a word. You just say the first word that pops into your head. Ready? Day.
Day. After day, the Earth is worn down by water, ice, wind, and chemicals.
Night.
Night. After night, the process continues, relentlessly, unabated, pounding on the Earth.
Interesting. Dog.
Doggone it! That mountain used to be higher and more jagged.
Aha! I think I see the problem. It goes back to your childhood. You are obsessed with erosion.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
Brought to you by Erosion Demolition, Inc. Give us the time and we'll wear away anything you got.
Rocks are solid. They're rocks. But every rock on the Earth's surface will be different tomorrow from the way it is today. They're eroding. Water, ice, wind, sand, and chemicals are constantly crumbling mountains, flattening hills, widening valleys, and deepening canyons. Erosion never stops. Never! Whoa! Wrong way. Take a look at this. It's our water flow erosion model of science. It's a piece of mineral salt and a hose. Now watch what happens when a stream of water slowly flows over it. It's changing. The water is carrying some of the solid away. We say it's eroding. Now this takes time. This is our expanding ice bottle of science. When we freeze the water inside with this ordinary household liquid nitrogen, the liquid water turns to solid ice, and it expands. It can split the bottle right open. See? Now, when liquid water gets in cracks and rocks and freezes, the rocks split open. This is another cause of erosion. Well, it's coming along. See, the rock is changing. Very, very slowly. Changing. There we go. Zip up. Now look at some wind erosion. This is sand. This is a sandblaster. Let's say that these plastic foam mountains are, mountains. Yeah. What? See, every particle of sand carries away a little bit of mountain. So that after a while, the mountains change. They're eroded. Okay. Thought I fixed that. Hello? Hello? Anybody?
Got a chip on your shoulder? Slough off life's worries the natural way at the Erosion Spa. Let our staff of skilled erosionists chip away and take off life's craggy peaks. Enjoy a wind and sand exfoliating scrub. Relax in an acid rain soak and smooth away wrinkles in the chemical erosion chamber. So when you're feeling jagged and unstable, set aside lots of time and come on down to the Erosion Spa.
Anybody? Huh? Okay, I'm gonna tap real hard. Phew. Sand in my mouth.
Look, the water has worn a little canyon. See how deep it is? Landscapes all over the world are always changing. It's erosion.
When it rains, the water that falls erodes the earth. Here's an experiment you can do to see how erosion works. Put some damp sand in a container like this. Dump it out like you're making a sandcastle.
Nice move.
Put a quarter flat on top of the sand. Sprinkle some water on top of the sand very gently.
What did you say again?
I said gently.
Oh, yeah.
See, the sand washes away in every place except underneath the coin. The coin is like a plant, or a tree in the forest, or a really hard rock, which helps prevent erosion. When there's something holding the soil in place, it doesn't erode as fast.
See this dark color? It's iron oxide, rust. There's iron in the rock. Rainwater and oxygen in the air combine to turn it into rust. It leaves these dark streaks on the rock. Let's say this is a rock. Well, it is a rock. And let's say that this is iron. Well, it is iron. It's steel wool, which is mostly iron. This is hydrogen peroxide, a chemical made of water and oxygen. As it flows over the rock and hits the iron rusts and leaves streaks, just like the streaks on the rocks outdoors. It doesn't matter if the metals in rocks are in human-made objects. Rainwater and fog are helping this metal combine with oxygen in the air. It's turning this copper green. It's slowly eating the metal away. It's just like the rocks. The iron turns to iron oxide. It's taking some of the iron out of the rock. Some of the rock is going away. It's a form of erosion. It's chemical erosion.
Tonight on Erosion.
What's this? Statue of Liberty. Worst example of chemical explosion I've seen in years. On my count. 1, 2, 3. Oh my gosh, the oxidation. This copper is entirely green. Somebody get the polish. Code green, stat. I think we can make this one in time.
When you have layers of different kinds of rock, erosion can happen from the inside out. If softer rock happens to be underneath harder rock, we can end up with a shape like this. softer rock erodes away first, leaving an arch.
Quit monkeying around, Bill.
As the wind blows across the high desert, it picks up sand. The sandy wind erodes these rocks.
A highly magnified view of several sand grains shows their sharp cutting edges. Such hard quartz grains cut into solid rock when blown across its surface.
Since the wind can only pick the sand up so high, it only erodes the rock so far. We call these mushroom rocks. They're formed by wind erosion. A stream has cut through this sandstone. The running water picks up sand grains off the stream bed and carries them along. The sandy water acts like a scouring pad, wearing its way down, year after year, year after year, year after year, and carving this canyon.
Erosion is the slow wearing away of the Earth's surface. Kind of like what I'm doing here, but for millions and millions of years. Yes, millions and millions of years!
Waves are relentless. They pound, 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 pound on the shore. And when they do, the force of the wave bends the rock and makes it crack. The continued force of the wave makes the cracks get bigger. And eventually, pieces of the rock fall away, leaving these. They're called sea stacks. That rock, in fact, all the rocks around here, used to be part of this hill. But the force of the waves has knocked them all loose. And I'll tell you what else. Another few million years, all of these rocks will be reduced to sand. Sand like this. See, here at the beach, the waves have been pounding on the pebbles and making them rub on each other for tens of thousands of years, turning them into grains of sand.
Now, when you look at the shoreline, you can see that it's a narrow strip of sand. That's because the waves only pound their way so far inland. But look, they're turning rocks into sand, for crying out loud.
It's erosion.
Welcome back to Pet Rock Theater. Tonight's episode, Grandpa smooths things out.
Grandpa, how come you're so smooth and I'm so rough?
Why, you just haven't undergone much erosion yet.
Erosion?
Here, let me show you. When I was your age, I was a little rough around the edges too. But after millions of years of sand, wind, and waves pounding on me, I got smoother. You will too.
Wow! You mean I'll be smooth like you?
Righty-o.
Will I have a gray beard and red iron oxide streaks too?
If you're lucky.
Nice view, but at what price? This house is built on the side of a hill, an eroding hill, and it's steep. When the soil got soaked with rainwater, it broke loose in big slabs. Now, if a house happened to be built on a slab and the slab came loose, well, the house went with it. Now, people can slow erosion down by designing concrete barriers, putting up plywood fences, and installing drainage pipes. They have to do all this extra work to live here with this great view. It's a choice they make. But sometimes they have to move because fighting erosion can be an uphill battle.
Tonight, on a very special episode of Eroda.
Hey, vey! This whole city just ain't what it's cracked up to be. Huh.
Can a single girl make it in a big city that's eroding before her eyes?
The seed that this tree is growing from landed in a tough place a long time ago. Now, right now, the roots up here are holding back rocks and soil. And the roots down here are strong enough that as they grow, they can split rock apart, helping break it down into soil for other plants to grow in. See, this tree is holding back soil. but the rock is still eroding away. So in one way, the tree is slowing erosion down. But in another way, it's speeding erosion up. See, living things are part of the process.
Tonight on MacGoober. MacGoober is trapped in an abandoned warehouse. But don't think he's licked yet.
I'm not licked yet.
Erosion. Now I just have to sit back and wait for erosion to dig through the floor.
Erosion girl, she'll wear you down. Rain, wind, and sand are blown around. She's erosion girl, and she'll rock your world.
Look at this! Look at this! It's erosion! Erosion! Rain, sand, ice. It eats away. It attacks rocks and mountains. It takes millions and millions and millions of years. It never ends. So suck it up and deal with it!
MacGoober.
Oh, yeah. Now we're getting there. Another 10,000 years ought to do it.
Don't miss MacGoober on Nye TV right after.
See these layers? This hoodoo. See this little arch? See this window? See those grottos? See these rocks? Well, take a good look, because they didn't look like this yesterday, and they won't look like this tomorrow. In fact, they'll never look exactly like this ever again. Here's why. Every once in a while, it snows around here. Then in the morning, the sun melts the snow, and the water flows down between cracks in the rock. Then at night, it freezes again and expands. That forces the rocks apart, makes them crack. Now, as the liquid water flows over the rock, it dissolves some of the minerals. That's why we see these different colors. Then this green color and this black color are plants called lichen, and they're feeding on chemicals in the rock. So the freezing water, the chemicals, and the living things are all eating away at the rocks.
Mm-hmm. You hungry, Bill?
It may not seem like it, but this process is happening every day. It doesn't ever stop. The walls of this canyon erode about that far, this much, about half a centimeter every year. Well, how far do you think they'd erode in 100 years? It'll be about that far. Well, then in 100 centuries, it'll be close to a soccer field. Well, just think what would happen in 1,000,000 years or 15 million years. You can see that one day, this place won't look anything like the way it does now. You see, erosion is a never-ending process.
When water freezes, it expands, and that can cause erosion. Try this. Take some modeling clay and smooth it into a ball.
A little faster if you could.
Like this.
There you go.
Put your ball in a plastic bag and place the whole thing in the freezer overnight.
All right. The next day.
Let it thaw, and then place it in the freezer overnight again.
Mm-hmm.
Then let it thaw and freeze it again. Now I've frozen this piece 3 times.
I know.
See, the clay cracks up all over the place. Water in the clay froze, it expanded, and then split the clay apart. Same thing happens with rocks. Water gets in the cracks and freezes it into ice. The rock erodes a little bit more every time the temperature dips below 0. It's erosion.
See the crack in that wall?
Uh-huh.
Hoodoo in progress.
Hoodoo.
That's a hoodoo, a column of rock. It started out as part of a vertical rock wall like that one. Then year after year after year, year after year after year after year, water worked its way into cracks and froze. It made big wedges slough off, leaving hard rock behind. The hoodoos, they're spectacular. Hoodoo! 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 Hoodoo!
Every mountain, rock, and hill wears away, erodes until it's sediment or sand carried off by rain and wind. Ooh, it's a change that doesn't happen fast. That jagged edge won't last. Pounding water, wind, and ice over falling rain. They're all causing the erosion. Even chemicals we know that are in the air. They're all causing the erosion. Surface of our planet Earth, each mountaintop and rocky cliff, eroded by the elements. It's a well-known fact. Pounding water, wind, and ice over falling rain. They're all causing the erosion. Even chemicals we know that are in the air. They're all causing the erosion. Pounding water, wind, and ice over falling rain. They're all causing the erosion. Even chemicals we know that are in the air. They're all causing the erosion.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some benefact abrasion coefficients to delineate. See ya!
Produced in association with the National Science Foundation.
Woo-hoo, steep! Whoa, sure it's steep. It's been washing for thousands of years. Look at this. Oh, man. Look at these things. Look at the size of these things. It's kooky. They're beautiful. The ventifaction that happens every day this time of year. Look at this huge wedges of material that get sloughed off every morning. Not every morning, but I mean slowly. You're looking good, but you know, another 1,000 years, I don't think you're gonna be here. Yep, I think you're gonna be long gone. There you are. Nothing I can do about it, my friend. You're a rock, I'm a human. You'll be here after I'm gone, I guess, but I can see it coming for you. Yeah, I can. Let's look over here. In your neighborhood right now, there's erosion going on. And this scene today will never be exactly like this again. Because it's eroding.
Universal Pictures presents Godzilla vs. the Comet.
Run away! It's Godzilla!
Nothing can stop Godzilla! It seems the superheroes are ineffective in combating the monster! Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
You and I live on a planet with a moon. Now, there are lots of planets with moons, and they all orbit the sun. But they're not the only things orbiting the sun. There are also tons and tons of rocks and ice, comets and meteors. When you see a streak of light in the sky, well, that's a chunk of rock burning up in the Earth's atmosphere, a meteor. When you see a star with a fuzzy tail, That's a dusty chunk of ice heated by the sun, a comet. Now, comets and meteors are all through the solar system, but most of them are way out there, past the orbits of all the planets. So far out that our own sun looks about like any other star. Now, comets and meteors are made of the same stuff as the planets. They were formed about the same time, and they go around the sun just like we do. Comets and meteors are part of our world.
What you got?
Nothing.
That's Tickle Me Meteorite, isn't it?
Nuh-uh.
Come on, let me see it.
No way! Get your own.
Aw, please.
He's so groovy, he's out of sight. He's Tickle Me Meteorite.
Yes, it's Tickle Me Meteorite.
You just pull his nose.
I have existed since the beginning of the solar system.
Here, let me try.
Comets and meteors travel vast distances in space.
Let me hold him.
Occasionally, meteors impact planets and moons, leaving deep craters on the surface. There is a theory that a meteor impact led to the extinction of the dinosaurs.
He's Tickle Me Meteorite.
It's Tickle Me Meteorite. Catch it fast before this offer burns up and disappears.
Good evening. Our next story is about elliptical orbits. This is the Earth. It takes a year to go around the sun, and its orbit is an ellipse. This is the orbit of a meteoroid. Many of them go out beyond the orbit of Mars. Now, this orbit is also shaped like an ellipse. This is the orbit of a comet. It's a very elongated ellipse because it takes comets such a long time to go around the sun. Most of them start their journey way out here, way out beyond the orbit of Pluto. Now, different comets have different orbits, depending on where they come from and what they're made of. It might take one comet 76 years to go around the sun, another comet 100 years, or 1,000 years, or tens of thousands of years. But all of these bodies, the planets, the meteorites, and the comets, are held in orbit by the pull of the sun's gravity, and all of their orbits are ellipses. Thank you.
Hey.
Comets travel in paths around the sun called orbits, but a comet's orbit is in a circle. It's a shape called an ellipse.
What?
An ellipse.
Could you say that one more time?
Ellipse.
Gotcha.
You can make an ellipse at home. Take 2 push pins and stick them about 30 centimeters apart on a piece of paper. Make sure you've got cardboard behind the paper. Then tie a knot in a string that's about 50 centimeters long. Put the string over the push pins and using a pen to keep the string pulled tight, draw all the way around the paper. Comets travel around the sun in paths shaped like this. It's an ellipse.
What?
Knock it off.
Recently, scientists photographed a string of comets slamming into the planet Jupiter. They started out as one big comet, but the pull of Jupiter's gravity is so strong, it broke them up into smaller chunks. Now, I say small, they were each a few kilometers across, and they slammed into the planet at over 60 kilometers a second, leaving big black spots the size of the Earth. The size of the Earth! Now, if one of those cometary chunks had hit our planet, well, we wouldn't be standing here talking right now, I can tell you that. Now, this photo opportunity on Jupiter wasn't a big surprise. See, scientists saw it coming and charted its course for years, which is good. because if we can predict the orbits of comets, then we can figure out whether we're in the clear or we should start worrying. So right now, as far as we can tell, we're in the clear for the next 1,000 years or so.
Meteoroids are chunks of rocks and metal that orbit the sun.
Comets are chunks of ice and dust that also orbit the sun. Excuse me.
So there's meteoroids and comets.
Excuse me.
When you see a rock fall out of the sky and land on the Earth, you know it's a meteorite. Now, the first thing you do when you analyze any rock is look them over. You can see that the edges are rounded and they're deep pock marks caused by the friction of passing through the Earth's atmosphere. On top of that, it's magnetic. It's made of metal. Now, this one has hardly any metal in it at all. This one turns out to be a combination of both rocks and metals. We know because we sliced it in half and polished it. You can see that this doesn't look like any of the rocks we find on Earth. Now, these over here don't look like any of the other three. It turns out that both of these are from Mars.
The meteorites. And there were signs and portents in the sky. People from coast to coast began seeing something up there. Visitors from outer space.
This is a meteorite from outer space. Looks like a mirror here.
This probably would have made a big crash when it hit the ground.
It's really heavy and it's rough. I can't believe it weighs this much.
This meteorite is special because it's from Mars.
We know it's from Mars because it has little bitty pockets that have gases from Mars.
Micrometeorites are so common that hundreds of millions of these fall to the Earth every day.
And you can find them in rainwater and in your backyard.
Congratulations, you found a micrometeorite.
It gives you a weird feeling holding things that have been flying through space for billions of years.
The following story is true and reflects events as they actually occurred. Once upon a time, a rock was orbiting the sun. Oh, about the time the solar system was formed. Then, one day, 16 million years ago, the rock slammed into the surface of Mars with enough force to knock a piece of the Martian ground into space, with enough speed to escape the pull of the planet's gravity, with enough speed to escape the planet's gravitational pull. Eventually, it crossed the path of the Earth's orbit at precisely the moment the Earth was passing through that sector of space. The rock came hurtling into the Earth's atmosphere, and aerodynamic drag caused the surface of the rocky meteoroid to ablate. To burn up, because it was hot. Ablate. A tiny fragment of that meteoroid made it almost all the way to the surface of the Earth, 2/3 of which, I remind you, is covered with ocean. 2/3 covered with ocean. Yet that meteorite found its way to a narrow strip of land near Nakhla, Egypt, where an unsuspecting dog happened to be going for his daily walk. The meteorite hit the dog and killed him, like that. Let's face it, my friends. That was one doggone unlucky dog. And as we say in science, he never knew it hit him. I remind you, this story is true.
Tonight on Nye TV, Little Meteorite on the Prairie.
What is it, Pa?
That's a meteorite, Half-Pint. Not a big meteorite because it probably got burned up going through the atmosphere. It's a little meteorite.
Wow. Pa, so what you're saying is that this meteorite came from outer space, and now it's on our prairie. It's our little meteorite on the prairie. Can we keep it? Will it hurt us?
No, half pint. Just burn up metal and stone.
Do you think it's got any iridium in it?
That might have pint, it might. Sometimes they're indistinguishable from terrestrial rocks. They have iron and nickel, and well, yes, iridium is much more common in meteors than on Earth's crust, which might help to explain the extinction of the dinosaurs.
12, maybe 20 billion years ago, there was a huge explosion, what scientists call the Big Bang. Within minutes of the Big Bang, tiny particles came together to form gases like hydrogen and helium. Then gravity brought those together to form stars. Well, then about 6 billion years ago, many of those stars had so much pressure built up inside them that they exploded. And we call each explosion a supernova. Anyway, that material drifted through space, and then eventually gravity brought it together to form our sun and all the planets. Now, at the same time, the comets, asteroids, and meteoroids were formed. So when we look at a meteorite like this one, we're looking at a rocky, icy, cosmic time capsule. It's cool.
And the quarterback drops back in.
Whoa! Whoa! Look at that flash! Oh, my! It's a meteorite or something!
Why isn't the Earth covered with craters the way the moon is? Please consider the following. When a meteoroid heads for the moon, there's nothing to slow it down. So wham! It makes a crater. When a meteoroid heads for the Earth, it has to pass through at least 80 kilometers of thin air. Rub your hands together. You know they get warm? That's friction. Well, meteoroids are going so fast that the friction of the air makes them heat up. Now, you may not know this, but metal burns. This is a piece of steel wool. It's mostly iron, just like a meteorite. If it were to hit the Earth's atmosphere, it would start to heat up. Now, the faster it's going, the more oxygen it passes through, so it really heats up, like this. Now, most of the meteoroids that hit the Earth's atmosphere burn up completely, but not all of them. See, you can still find meteoroid craters on the Earth's surface if you know where to look. Like, this is Meteor Crater in Arizona. This is Manicouagan in Quebec, Canada. This is Kalakul in Afghanistan in Asia. And this is Basumtwi in Ghana, Africa. Now, these meteorite craters are huge, and there's still hundreds of them on the Earth's surface. But wind, water, ice, and volcanoes help smooth them over. See, every planet and moon in the solar system has been hit with meteorites. But not all of them have a nice atmosphere to protect them. Well, thank you for joining me on Consider the Following.
When comets and meteors hit a moon or planet, they can leave a crater. You can see craters on the face of the moon.
Excuse me.
A meteorite impact on the Earth's surface. So how do we know that this big hole, this crater, was made by a meteorite? Well, here's the evidence. First of all, its shape. It's almost perfectly round. And it's big. It's huge. Whatever made this hole must have been big. Now, when we look at the rim, the edge of the crater, we see that it's higher than the high desert floor around here. Something must have lifted that material up. When we look at the surface of these rocks, something made them change from this color to this color. Well, it turns out it's heat, pressure, being mashed and squeezed and mushed. So something must have mushed and squeezed this rock. Now, on top of that, this white rock is not normally on the surface. We don't find it around on the high desert floor. But there is a layer of white rock underneath a layer of red rock in this crater. So something must have mushed and squeezed these rocks and lifted them up on top of the red layer. It turns out that this big hole, this crater, was made by a great big rock, a meteorite from outer space. Woo! When we look at the far side of the crater, over there, we see that it's higher than the rim where we're standing. So we figured the meteorite came from that part of the sky, like this. Boom! It was going so fast that it could have made it from those mountains over there, 30 kilometers away, to here in less than a second and a half. It would have been like 1/1000.
We now return to Leave It to Meteor.
Ah, geez, Meteor. Why do you gotta go lugging around that hunk of rock?
It's not just a rock. It's a meteor. Besides, I like playing with it.
It's only a meteor when it's in the atmosphere. After it lands, it's called a meteorite.
I know, Wally. But if my nickname were Meteorite, the kids would razz me for being a goof.
Who's the goof now? Dad's gonna burn up like space dust entering the Earth's atmosphere.
It's Comet Hale-Bopp. We were able to see it for about 3 weeks. But by the time you see the show, the comet will be gone. Long gone. Back into the cold, dark emptiness of space. Bah! Huh. Hi, I'm Bill. That's Comet Hale-Bopp.
Yes, I'm Hale. And I'm Bob.
It's ice that makes comets different from asteroids and meteoroids. As a comet gets near the sun, the heat of the sun and the solar wind vaporizes the ice and makes a stream of charged gas particles we call the ion tail. Now, at the same time, the little bits of rock that are embedded in the ice get blown into space and form a second tail we call the dust tail. It's made of thousands and thousands of tiny meteoroids that orbit right along with the comet. So we end up with an ion tail that points straight away from the sun and a dust tail that's a little bit curved. So we get two tails from one comet. It's two tails from one. An asteroid is a big chunk of rock in space that never became part of a planet. A small asteroid is called a meteoroid. Now, if a rock enters the Earth's atmosphere, starts to burn up and leaves a bright streak in the sky, we call it a meteor. If a piece of that rock lands on the Earth's surface, well, then we call it a meteorite. Asteroid, meteoroid, meteor, meteorite, right?
There are so many comets and meteors in the sky, but we only see a few that fly close by. When they're on a course that brings them too near, they start to burn if they hit the Earth's atmosphere. Might make it all the way to the ground. Might make a crater big and round. Comets and meteors got me looking up into the sky now. They're made of dirt and ice, you know they're in orbit around the sun now.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some subcrustal crater cartography to collate. See ya!
Produced in association with the National Science Foundation.
Did you ever make a wish on a shooting star? Well, guess what? They're not stars at all. They're meteors. Most of these meteors don't even make it to the Earth's surface because they burn up on their way through the atmosphere. We see them burning up as streaks of light. On any given night, there's a meteor flashing across the sky about once every hour. So the next time you see one, instead of making a wish on a shooting star, make a wish on a blazing, burning meteor.
Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
If you've ever been in an especially strong wind, or if you found yourself in a blizzard, or a downpour, or if you've ever heard thunder, or seen lightning, well, that means you're in a storm! Storms happen all over the world every day. Without storms, life wouldn't be anything like the way we know it. The world's air and water wouldn't be nearly as bad. Oh. Storms are extreme weather. They're caused by the heat of the sun, water in the air and the spin of the Earth. Take a look at this. It's our miniature, gigantic, extreme storm system simulator of science. Now, when the sun is out, like during the day, it heats up the surface of the Earth, as simulated by these red lamps. That makes the air near the ground get warm. Then cooler air from surrounding areas flows in and forces the warm air way up, like this. Now, way up, it's a lot cooler because it's closer to space. So we get this flow of air moving up and down at the same time. These are the conditions that make storms. Now, we're simulating a lot of sunlight over an enormous area of land with huge masses of air. Now, in real life, the air flows in from different directions, so it can start to spin like this. Wherever you've got heat, an atmosphere, and a spinning planet, it really churns things up. Storms are extreme weather. Extreme weather!
Welcome to Extreme Weather Theater. What, you ask, is extreme weather? Well, this is extreme weather. Thank you. This, too, is extreme weather. Thank you. So is this. Thank you. This has been Extreme Weather Theater.
Storms are extreme weather patterns, baby. They'll soak you rotten.
From time to time, a mysterious thing occurs over the eastern Pacific. It affects the weather worldwide. It is El Niño.
El Niño.
Normally, trade winds blow over this part of the ocean, keeping it cool. But from time to time, it stops. Then the sun beats down, warming the sea, which warms the air. And no one knows why. It is El Niño.
El Niño.
When this happens, fish die. Fish die. And storms rage all over the globe. It is El Niño.
El Niño.
Now, I must go. Adios, amigos.
El Niño.
Unseasonably warm and stormy weather we're having at this time of year, don't you think?
This strange weather phenomenon, my friend, is the work of none other than El Nino.
El Nino?
El Nino. A mysteriously warm area of water in the Pacific. It can affect world weather patterns, causing unseasonably warm weather and more frequent and powerful storms. El Nino.
On planet Earth, there are storms the size of Texas, hurricanes and typhoons. They're formed when huge areas of the open ocean soak up a tremendous amount of heat from the sun. Cool air squeezes warm air up. Warm air carries water vapor with it. When the vapor turns back into a liquid, when it rains, it releases a lot of energy high in the atmosphere, which helps drive the winds of the storm. These storms are so big that they get spun by the spin of the Earth.
More energy being released every second than from a dozen atom bombs.
Now, the winds are moving so fast that these storms end up with a hollow spot right in the middle called the eye of the storm. The winds are calm there, while they're really howling around the outside. Now, if one of these storms moves from the ocean onto the land, they can really tear things up. Uh-oh.
When a cold air mass meets a hot one, look out, baby. It's stormadelic.
Hey, there aren't any anchovies on this menu. What's that all about? Oh, no. Not...
The missing fishies, my young friend, are the result of mysteriously warm waters killing creatures like your precious anchovies from Alaska to Peru. It is none other than El Nino.
Lightning is electricity, the flow of electrons. Now let's say that these people are electrons. They're all negative. They have the same charge, so they're repelling each other. Right now, there's nowhere for them to go. But when the door opens, they spread out. The same thing happens in clouds. Let's say this is a cloud, and this rubber belt is keeping it chock full of electrons. Now, they'll spread out if we let them. They spread out! The easiest way for them to do that is to find a path to the ground, like this. Oh no, it's a big dark storm cloud coming our way! Quick, everyone, get in the house! Pow! A bolt of lightning. Now, the lightning heats up the air and makes it expand so fast, it's like an explosion. Thunder. And thunder can get pretty loud. See, we were going to make my bones light up, like in the cartoons. But instead, we went with this makeup effect.
When you're caught in a thunderstorm, a tree may look like a nice shelter, but it's not. Since lightning strikes the highest point around, a tree is a prime target. So don't stand under a tree during a thunderstorm.
What you should do is get short and make as little contact with the ground as possible, so the electricity is less likely to choose you as a path than, say, if you were under a tree or standing in the field or lying flat. So just squat like this and let the lightning find something else to hit. It may feel a little uncomfortable, but it beats getting zapped.
I bet those kids downstairs are shaking in their shoes.
Huh?
You know, whenever angels go bowling, we make thunder.
No, we don't.
We don't?
No. Thunder is caused when charges due to static electricity are built up in the clouds and the surface of the planet. When the difference in the charge is big enough, pow! You get a bolt of lightning that instantly heats the air up to 5 times the temperature of the sun. That creates a sound wave known as thunder.
Well, gee, all this time I thought my 710 splits were the cause of explosive sound. Well, they're sure gonna get a rainstorm down there.
Huh?
I'm gonna cry. And when angels cry, the rains come.
About that rain thing, we need to talk.
Tornadoes take place when air masses of extremely different temperatures come together. See, the sun shines right through the air and warms the land. The land acts like a stove and heats the air above it. Now, instead of the hot air getting squeezed and rising, it's held down by a slab of cold air. So if conditions are right, the hot air punches a hole through the cold air and rushes up through it like a bathtub drain, upside down. If that happens, take cover, my friends. You got yourself a twister. When that happens, my friend, take cover, because you got yourself a twister.
Some storms spin because of the Earth's rotation. Oh, behave, you little twister.
The stuff we have here is our most recent area of research, and it involves work at the University of Colorado to model tornadoes in the laboratory. We chose water because water and air act the same way. You can work with either one of them and get good results. We discovered that some of these lab tornadoes make very, very loud sounds. And we're trying to understand that because we've discovered that full-blown tornadoes in the atmosphere also make sounds. But when we deal with real tornadoes, the sound we're expecting is going to be so low that we require an electronic ear to hear it. This is our electronic ear. All of these hoses that are going out from it, like an octopus's tentacles, are the sensing element that all feed into this microphone. All storms are really potentially dangerous in some way, but we might be able to listen to sounds that could save lives.
You can see how a tornado works. Just fill up 2 2-liter pop bottles.
These plastic ones are cool because you can do that.
So have a so-called friend help you fill up the bottles. Have a friend help you empty the bottles. Make it a race. Tip the bottles over at the same time. Keep one bottle steady and give the other one a twirl. Ready?
Okay, go.
See, when you get it spinning, the water drains much faster. The same thing happens with tornadoes. When air gets spinning, it spins faster and faster to make a wild, spinning storm.
I won.
The Earth isn't the only place with storms. No, they happen all over the solar system. This is the planet Jupiter. It's over 1,300 times the size of the Earth. And for hundreds of years, astronomers have observed a great spot. It's a storm, a hurricane. And it's over twice the size of our planet. It's been raging for hundreds of years. And you're saying, well, why doesn't it die down the way hurricanes do on the Earth? Well, there's two things. First of all, Jupiter is huge.
Jupiter, twice as large as all the other planets combined.
Secondly, it's spinning very, very fast. It takes Jupiter only 10 Earth hours to go all the way around. So the winds on the surface of Jupiter are really moving. They're going fast enough to sustain this gigantic storm for centuries on another planet. Wow.
There's the sun up in the sky. It's heating places all around at different rates, so wind is made and water evaporates into the sky. Storm clouds forming in the sky because cold air pushes warm air way up high. Robert has been falling lately. The storm is on the way, and baby, we should all get ready, baby. Here comes a hurricane. Now we're wet, the rain is pouring. Look out, cause the wind is blowing. Cold and warm air mass is flowing. It's all mixing up the atmosphere.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some mesocyclone advection currents to quantify. See ya!
Produced in association with the National Science Foundation.
Gonna get right into the lifting condensation level. Right on, right to the meter. The half meter. And that way we'll know for sure just what induced this blizzard. Yeah. As the air goes up, and then after a while, it goes down!
I'm buying lunch today. In fact, I'm feeling pretty good. I'm buying lunch for everyone. Hey, everyone! Lunch is on me.
I'll take a steak to go!
Extreme weather! Wow!
Storms.
Extreme weather!
Storms.
Extreme weather! Wow!
Welcome back to Measuring for Dollars. Brought to you by Baby 04.
I'll take increments for 100.
The answer is unit to measure the diameter of an atom.
What is an angstrom?
Yes, still your turn.
I'll take hurry up and weights for 200.
Word used to describe weight of precious stones.
What is a carat? I'll take potluck for 500.
Ooh, a 20-letter word for a cool science show. 20-letter word for a cool science show. Anyone? Oh, sorry. What is
Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
How far is it from here to here? How much does the television set you're watching weigh? And how many years old are you? See, we measure things all the time. That's how we compare one thing to another. Measuring things is how we understand the world. And especially, it's how we understand our place on it. Measuring things allows us to figure out how long it takes to get from one place to another. If we didn't measure things, everything we build would fall right down. The better we measure, the better things fit. Take a look at this. It's our very wide chasm of science. We want to build a bridge from here to there because the chasm is too far to jump across. And besides, down there is a raging river infested with vicious alligators. Well, it's a representation. So, to build a bridge, we need to measure it. When we measure things, it's as though we project a grid on the world. So we can measure this empty space with this 2-meter stick. And it's exactly 194 centimeters across. So, we want a bridge at least 194 centimeters long, but not too long because we don't want the bridge to run into these very dangerous high-voltage power lines, which are a little over 2 meters away. So we'll make a bridge that's 194 centimeters. Well, here's one we prepared earlier. Let's measure it. And it's 194 centimeters. So let's lower it and see if it fits. Here we go. See, we knew it would fit because we measured it first. Now we can cross the chasm without fear of the alligators.
Guess you made a little miscalculation there, Bill.
Just kidding.
Oh.
Measuring allows us to make things that fit, and we can understand the world. We don't come up short! We can measure all kinds of things that are going on in the human body. Our heartbeat, how much oxygen is in our blood, even our brain waves.
Very interesting.
That's how we understand what's going on inside. Now, the more we want to know, the more measurements we make. Every post, every beam, every pillar, every pipe, and every wire is planned. We know where they're all going to go because we measure them beforehand and we measure them as we put it together. The more carefully we measure, the more accurately we can make things and make things fit, like airplane parts. First, we line the machine up. Then it can find its way to anywhere it can reach within half the thickness of a sheet of paper. We can make each part just exactly as heavy as it needs to be. That way we can make planes that fly farther and faster and use less fuel. The better the measure, the better the plane. Here we go. Woo-hoo. Okay, once we're flying, we use these gauges and instruments to keep track of things we need to know, like how fast we're going, how high we are, how much fuel we have left. That way we can measure things and land and fly planes safely every time.
Oh, boy. The nose is too high. I'm almost out of fuel.
Bill.
We're not going fast enough.
Bill,
Whoa, we're losing
slight
left.
overcorrection, Bill.
Pull back.
Bill.
No, forward. No,
Great moments in measurement. A long time ago, people used to measure things with their own body parts, like feet. But just whose foot was 1 foot? Later, it was the king who declared that his foot, the royal foot, would be the foot that all feet would be fitted against. It was the standardization of the foot, and it was quite a feat.
Humans are about this big, so we've always wanted a unit of measurement about this long. And we want it to be the same for everyone. We want it to be a standard. That's why it's hard to use something like a foot, because not everybody has the same size feet. So what we did is we looked at the Earth, and we divided the distance from the North Pole to the equator in tens, 10 million times. And we got this. It's a meter. We use tens because humans have 10 fingers. Now you can keep going. You can divide a meter by 10 and 10 again, and you get centimeters. There are 100 centimeters in a meter, just like there are 100 cents in a dollar. You can divide it by 1,000, and you get millimeters, by 1,000,000, and you get micrometers. It's easy. With a meter, you can measure just about anything. This microphone is about 32 centimeters long.
What?
It's the metric system. It's easy.
What?
I said it's easy.
What?
The man with the accurate touch. It's the power of
007. Point 007.
If you're going to go up against the more sinister elements, you're going to need one of these, the ultimate measuring device.
Does it have a death ray?
Please try to be serious, Point 007. It measures temperature, length, time, and if you stand on it, it will even indicate weight.
That's fantastic. All the things humans need to measure.
Precisely. Please try to bring this one back intact, will you, Point 007?
I'll do my best.
A bulb from Baltimore screws into a socket in Seattle. A battery born in Boise can relocate to a radio in Reno. A cap fabricated in Fresno fits on a fizzy container of soft drink. Maybe in your hometown. But see, they all fit because they've been measured. It's fabulous.
Bill, don't touch.
She's gonna start a revolution. When she finds the solution. Yeah, when she launches, she's pure old-fashioned action. Even flies stand by for Citronella Jones.
Tonight's episode, just about a meter.
Federal Agent Citronella Jones, Bureau of Weights and Measures.
Come on, what I do? I'm clean, honest.
Honest! Sniffly, you don't know the long and short of the word. Just as I suspected. Counterfeit meter sticks. Hasn't anyone schooled you on the importance of standards, Sniffly? You can't just put random markings on there and call it a meter stick. It just doesn't measure up.
Oh, what does it matter, Citrina?
Freeze! No! I want you 0 degrees Celsius, mister. Same old story. I give you a centimeter, Sniffly, and you take an astronomical unit.
Oh, Citronella. Come on, give me a break, will you?
We use standard measurements. A meter in America. C'est la même chose qu'une mètre en France. Or a meter in Britain. Or even a meter on the moon. It's all the same.
We don't need much to measure just about anything. Please consider the following. We can measure the width of this board. It's 1 meter. We can also measure how high it is. It's also a meter. We say we're measuring the area of the board. It's 1 meter by 1 meter, or 1 square meter. Now, this board isn't as wide. It's only half a meter. But look, it's 2 meters long. Well, 2 halves make 1. So even though it might not look like it at first, this board and this board have exactly the same area, 1 square meter. We measured it, and all we needed was a measurement of length. Now take a look at this. We can measure the area of the end of this cube. It's also 1 square meter. But we can measure it this way as well. That's how high it is. When we do that, we're not measuring its length, but how big it is, how much room it takes up, its volume, and it's 1 cubic meter. So whenever we want to say how much of something we have, all we need is a way to measure length, like a meter.
Bill, you can lose the hard hat. I'll take care of it. Thank you.
Now here's the thing. Everyone has agreed that a tenth of a meter by a tenth of a meter by a tenth of a meter is a volume called a liter. Now, on top of that, a liter of water
Very nice. Careful.
See, a liter is exactly 1 kilogram. So if we want to know how much mass something has, how much it would weigh, all we need is 3/10 of a meter and water. It's easy. Like when you measure a distance, all you need is a meter. 1,000 meters is a kilometer. And 1,000 liters, well, that's a ton. Well, thank you for joining me on Consider the Following.
Try this. Make a hodometer. Take a ruler and draw a line that's 15.8 centimeters long on a heavy piece of paper.
Wait a minute. What's that? 15.8? That's 16.8. Uh-oh. Oh, you started at 1. Okay, I got you.
Use a tack and a pencil to draw a circle with the paper. Make 2 of them and cut them out. Here's 2 I prepared earlier. Use a brad to make a hole in the middle of each circle. Tape them together. Now attach the cardboard to a handle, like this. Use a scrap piece of cardboard as a guide for your wheel. Draw 2 arrows on your hodometer. One here, and one here. The outside of the circle is exactly 1 meter around.
Uh-huh.
Lined up and roll your hodometer. Every time the arrows cross each other, you've gone 1 meter. Measure things.
Good afternoon, you measure at frames.
Hey, what's up?
We have frames, you measure.
Hello?
Huh?
Hello, yeah. Yeah, I'm looking for a frame.
Yes, what do you need?
98 centimeters by 68 centimeters blue aluminum frame, please.
Oh, yes, we have a very nice
Yeah.
one.
Uh-huh. Yeah. Uh-huh. Mm-hmm. Yeah. Gotcha. Yeah. Uh-huh. Yeah. I can communicate the size of my poster and get the right frame for it. And I know it'll fit because I measured. Yeah.
Measure a soccer field. With your hodometer, you could, dare I say it, measure the world!
This is a thermometer. It has a liquid metal inside, mercury. It expands when it gets warm, and it contracts when it gets cool. And it expands and contracts the same amount each time. So we can use it to measure temperatures very accurately. Now, this is ice. It's cold. You can feel it. This is boiling water. If you touch that, you get burned. So an astronomer named Anders Celsius came up with the idea of using a thermometer. And he called the temperature at which water freezes 0 and the temperature at which water boils 100. So there are 100 degrees between ice and boiling. And to this day, it's called the Celsius scale.
Now we'll have occasion to make temperature measurements. So we need a standard of temperature, too.
Thermometers are cool.
Oh, I mean, they're hot.
Perfect. The things we measure most are length.
Mass.
Time.
And temperature.
The things we measure most are length.
Every time of day, everything you wear, every mark you make, every temp you take is a measurement. You trick. Keep using standard measurements. Standard measurement, time and mass and length, temperature you take, standard measurement.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some global positioning calibration algorithms to optimize. See ya.
There's latitude and longitude, and the Earth's spinning underneath it.
Produced in association with the National Science Foundation.
And we got this. It's a meter. We use 10 because humans have 10 fingers. It's easy. History books would be a lot harder to understand if humans hadn't discovered ways to measure time. It all starts with days, because every day is divided into a day and a night. Humans discovered that they're caused by the spin of the Earth. The Earth is like a giant clock that goes around once a day. Now, there are 365 and a quarter days in a year. So humans invented calendars to keep track of days. And we invented clocks to divide days into hours, minutes, and seconds. By measuring time, humans can record history, do things on schedules, celebrate birthdays, and just be on time.
Time's up.
Tell me what you see in these shapes.
That's a nautilus shell.
This one?
A spider web.
What about this one?
That's a snowflake.
Now, tell me what you see in this one.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill. Bill Nye the Science Guy.
Brought to you by the Incorporated Corporation of Repetition Incorporated. We give you the same thing over and over and over and over and over.
Look at these bees. They're building their honeycomb using the same six-sided shape over and over again. And see their black and yellow stripes? We recognize them as bees. And if you've ever been stung, you might make the connection between black and yellow stripes and danger. Watch out. We use black and yellow stripes to warn us of dangerous objects in the lab. It's a pattern. We recognize it. It repeats. We look for patterns. We see them. We smell them. We hear them. We live through them. Patterns help us organize information and make sense of the world around us. By finding patterns, we can predict the future, duplicate designs, and find our way in places we've never been. Take a look at this. It's our repeating roller pattern maker of science. Here are some patterns. This one represents the sun. These waves represent the ocean. And this moon is the moon. Now, as the roller turns, the patterns move. The moon is over here now, which scoots the sun and the ocean that way. Now the ocean's over here, scooting the moon and the sun. As the roller turns, the pattern repeats. The pattern repeats. The pattern repeats. 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 Repeats.
Okay.
Repeat. Now watch what happens when we run the roller through our great big ink pad of science. See, the same pattern repeats on paper because it was made when something happened over and over again. You okay?
I'm flat. Oh.
He's okay.
I'm okay.
There are also patterns in time. This is a model of the Earth, a globe. Now let's say you're a human living on the Earth, and you are. Every day you can observe a pattern caused by the Earth's turning. Sunrise and sunset. Sunrise, sunset. Patterns are how we humans understand the world.
Yeah.
Go on.
Hey, down here. Oh, do you have the time? No.
Sunrise, sunset, sunrise, sunset.
Hey, over here. Now back the other way. Now this way. Back. Oh, back. Come up. Look up. Yeah. Here. Right here. See? Hi. You had trouble finding me, didn't you? That's because I'm camouflaged. My clothing blends in with the pattern of my surroundings. Camouflage is from an old French word that means disguise. And animals use camouflage to help them survive. For example, zebras have a pattern of stripes that makes it hard for a predator to tell where one zebra starts and another one ends. That way it's hard for a predator to pick out any one animal to attack. And leopards have a pattern of spots on their fur that blends in with the dappled sunlight in the forest or jungle where they live. It makes leopards hard to spot. Hard to spot, get it?
Yeah,
leopards.
got it.
Some reptiles have camouflage that helps them sneak up on things they're going to eat.
Help! 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 Somebody help me! Rumple is stuck in the tree!
I can help.
Who are you?
I am Stripe Man.
Oh, Stripe Man! Am I ever glad to see you?
Did you know Stripe Man can baffle predators by running in a flock with other Stripe Men?
Wow! Can you fly up there and get Rumple?
No, I can't fly, but if there were predators around, I could confuse them.
Do you have superhuman strength to pluck the tree out of the ground and rescue Rumple?
No, I can't do that either, but my vertical stripes make me look thinner. I'm Stripe Man.
A lot of good that does Rumple.
Spirals. This is a nautilus. It's an animal that lives in the ocean, and it builds a spiral shell. See, as the animal gets bigger, it needs more space. And because it has a spiral shell, it can add a new room by building just one new wall. Now, when we go to build a new room on our house, we have to add 3 new walls, not to mention a floor and a ceiling. Not as efficient. Not as efficient. Now, spirals aren't always flat. They can go up, like this. Here's a spiral staircase. It doesn't take up nearly as much space as a long, straight stairway. It still lets us go up and up and up. Deoxyribonucleic acid, DNA, is a molecule that carries a tremendous amount of information. It's twisted into a spiral. That makes it compact. Spirals are efficient patterns.
A tie-dye is a pattern you can make. All you need is a t-shirt, rubber bands, and a box of dye. First, take the t-shirt and roll it up. Then, use rubber bands to tie the fabric tightly. Keep doing this until the shirt is tied up in blobs.
Here you go.
Here's one we prepared earlier. Follow directions on how to mix up the dye with a bucket of water. Here's some dye we prepared earlier. Submerge your shirt in the dye and hold it under with a stick. After a few hours, pull out the shirt, rinse it off. Now take off the rubber bands. Then when the shirt dries, you'll have a pattern that you can wear.
Try it! Dig it.
Dug it.
Science!
We use patterns to communicate. Patterns of gestures.
I love you.
Patterns of symbols. Peace, dude.
Half time!
When most of us see letters, we recognize patterns, called words, that convey meaning. People who can't see use patterns of raised dots to represent the same letters, words, sentences, and stories. It's a different way of reading the same pattern. Patterns aren't just things that we see. They can be things that we hear. Patterns of sound.
Now, there's a pattern we recognize. A ringing phone. Now we know to answer it. Hello? Oh, hi, Mom. Let me write it down. Say it again. Okay. Milk. Eggs. Bread. I got it. I got it, Mom. Milk, bread, eggs, yeah. Oh, okay, I'm on my way. Yeah, come. Yeah, love you too. Horns make a pattern of sounds that we use to alert other drivers. Car crashes have distinctive patterns of sound also. And then there are sounds that are used for warning, like dog barks, bear growls, and rattlesnake rattles. Of course, humans use sound for warning too.
Huh? Wow. Whoa.
Then there's music, which is a pattern of sounds we use for fun. Sounds, patterns, music.
Without space between my words, you understand a word I say, just hear gibberish. Without spaces in between my words, you wouldn't understand a word I'm saying. You just hear gibberish. To have a pattern, you have to have spaces.
And now for my greatest patterns. Diamond head. Butterfly head. And the crowning achievement, polka dot head.
One of the great parts of my work here at MIT is to sort of hold people's attention for a moment in the world of science, training your eye to look more at details about everything, because really understanding details gives you an incredible amount of information. There are patterns all over. There are patterns on a CD disc, on minerals. There are patterns in bubbles, in oil slicks, crystals, some of them made by hand, some of them naturally occurring. And computer chips, the way they put down the information, it's all about patterns. It's pretty amazing if you really start paying attention to the world around you, how many patterns you can see.
A long, long time ago, humankind foraged for food. But sometimes there were no berries to be found, and they went hungry. It was a tough existence. But then, humans discovered some patterns. They noticed that plants had a certain pattern of growth, from seed to growth to harvest to storage of the grain. They also noticed a repeating pattern in the daily temperature and length of sunlight. It was a pattern of seasons. Spring, summer, fall, winter. Once they realized these patterns of plants and seasons, the enterprising humans worked on matching them together. After much trial and error, the humans finally tasted success. Patterns that changed humankind forever.
You and I are living things. We're part of a great big family pattern. Please consider the following. Humans, scientists, put living things in groups. For example, here's a giraffe, which is a lot like a zebra, which is a lot like a horse. Now you know without looking that these animals have bones. And sure enough, horses have leg bones, rib bones, back bones, and skulls, head bones. So do we. But what do you make of these bones? They're from a dinosaur. Now, when you look at them, the bones aren't all that different from ours. They've got leg bones, rib bones, back bones, and head bones. Just like ours.
Watch it.
They fit the same pattern. But we can't really put these bones with these animals because there are no dinosaurs around. So instead, we put them back in time. See, we know that dinosaurs once lived because we find their fossils all over the place. And they're not the only kind of fossils we find. Oh no, we find insect fossils, reptile fossils, plant fossils, and fish fossils. All kinds of fossils of creatures that once lived in the ocean. There are tiny microscopic fossils of ancient bacteria. Now here's the thing. When we look very closely at the DNA, deoxyribonucleic acid, chemical instructions that are in all of our cells, we find that all of these living things have the same patterns of chemicals. So near as we can tell, all of the living things on Earth came from just one kind of living thing which lived billions and billions of years ago in the ancient ocean, what we call the primordial soup. So we were looking for patterns in living things, and we discovered evolution. Evolution? We discovered a pattern in time. Whoa. Well, thank you for joining me on Consider the Following. I don't know.
There's a pattern.
You don't have to be an expert to find patterns in nature. You just have to look a little bit closer at things and not look from so far away. Inside the sunflower, you can see the spirals that it makes, and they get bigger and farther apart as they spread out.
For example, if you pick up this seashell, you can see all the different kinds of triangles in it. And whether they are big or small, they all look alike. Spirals on the top form the Fibonacci sequence, which is a sequence of numbers that happens to be found everywhere in nature that was invented by a mathematician named Fibonacci.
There's patterns in a lot of things, and broccoli's one of them. Broccoli's a good example of fractals. As you can see, when I break off a piece of broccoli like this, it looks a lot like the big broccoli.
Like with the fern, if you look at a fern, it'll have a whole particular shape, like a triangle. And if you take off a smaller part of the fern, it has the same triangular shape. You can go even smaller and break off another small part, and it'll still look the same as the whole fern. And that's called self-similarity, where all the parts of the whole thing look the same as it does itself.
Patterns aren't only found in nature. You can make your own, and this is a fractal, and this is mine.
You can even use computers.
There's just tons of patterns where you wouldn't expect them to be.
Daddy, fractals are pretty! Patterns are everywhere. You can see patterns wherever we build things. Patterns of triangles to stiffen structures. Patterns of offset bolts to keep the steel stronger. Patterns of welded wire to reinforce concrete. This is rebar. Rebar is a bunch of steel rods arranged in a pattern, and then a bunch of concrete is poured over it. See these grooves in the steel rods? They help grip the concrete and hold it together. It's a pattern! Patterns in construction!
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some cryptic coloration patterns to analyze. See ya!
Produced in association with the National Science Foundation.
Patterns.
Stripe Man could climb this ladder and bring back Rumple. And, by the way, did you notice this ladder is composed of a repeating pattern of parallel rungs?
Oh, Stripe Man. Oh, Stripe Man.
By the way, Rumple, nice pattern.
Patterns. If you know your patterns of stars, you can find your way around on the Earth's surface. Star patterns are powerful.
Science!
Patterns everywhere.
Science guy, what a genius! You are the greatest. Bill Nye the Science Guy. Bill Nye the Science
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
Hear that? Ah, it's music to my ears and to yours. Music can be a tune on a fiddle. It can be whistles blown to a beat, the strumming of a string, or a song played on the saxophone. Music is made all over the world.
Oh yes, I'm walking.
It's a pattern of vibrations in the air. And music affects our senses. Take a look at this. It's our musical sound wave vibration display of science. This is an electronic keyboard. And this is a piano. This is the display of an oscilloscope. It's a device that's connected to a microphone that picks up sound waves in the air and shows them to us here on the screen. Now, when I hit a low note, we can see that the waves are pretty far apart. When I hit a high note, the waves look about the same, but they're much closer together. This is true on the electronic keyboard or on the piano. Now, this is called the pitch of the sound. So this would be a low-pitch sound, and this would be a high-pitch sound. Now, we take these sounds and arrange them in what are called notes of music. Now, notes of music can be close together or far apart. Now, that's called the rhythm of the music. How close together the notes are and how long each note lasts. And there's one more thing. We can play a note softly or loud. So, pitch, rhythm, and loudness, they're all ways to make vibrations of sound that can become notes that can be arranged in patterns to make music. They could be arranged into patterns that become music. Depends on who's doing it, I guess.
Consists of two muscular strips called the vocal cord. As we force air up from the lungs, it causes the vocal cords to vibrate.
This is the difference between a musical note and a noise. Music is a regular wave motion. A noise is an irregular mixture of many wave motions.
Today on the Jackie Smash Show, it's the amazing juggling feats of Yoo-Hoo the Clown.
Jackie, Yoo-Hoo canceled. Now it's Bill Nye the Science Guy.
And my guest, apparently, is Bill Nye the Science Guy.
Great to see you again, Jackie.
What do you mean? Have you ever been on this show? He's never been on before, has he?
Yeah, once I think.
Lots of times. Yeah.
Let's cut the small talk here, Bill. I want to talk to you about ears.
Yeah.
How do these things work anyway, these ears we have?
Oh, we have two of them, most of us, and I prepared a little demonstration. Let me show you. Sound is vibrations moving through the air, like this. The vibrations make air molecules move. The vibrations come down this part of your ear to your eardrum, which flexes like the head of a drum, like this. Now, your eardrum vibrates at exactly the same speed as the vibrations of sound. That makes these tiny bones move, and they push on the end of the seashell-shaped tube called your cochlea. Tiny hairs toward the front of the tube pick up high-pitched sounds, and hairs deep inside the tube pick up low-pitched sound. They send signals through your auditory nerve to your brain, and we perceive them as sounds.
So, it's all done with vibrations then, huh?
That's right, Jackie, vibrations.
Vibes, baby.
Well, music is a pattern of sounds. Makes me want to move my body around. It's science, baby. A pattern of repeated sounds.
This is a tuning fork. When I hit it, both sides start to vibrate. 440 times a second. You can hear it when I press it on this fiddle. Now, the vibrating tuning fork is setting up vibrations in the air. Now, that doesn't mean that all of the air is moving like the wind. It means that the tiny molecules of air are tapping against each other. A little bit like this.
Uh-huh.
The vibrations move through the air. They find their way to your ear and to your eardrum. Your ear can detect the tiny movements of tiny molecules.
You can see sound waves for yourself. Just take a soup can and cut off both lids. Now use a rubber band to hold the plastic wrap tightly over one end. Then glue a sequin to the plastic wrap. Now turn off the lights. Shine a flashlight on the sequin. And then you sing into the can. Ha ha ha. Ba 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 ba. See? The shiny sequin bounces light onto the wall. When you sing, sound waves jiggle the plastic and shake the sequin. Music is vibration. Vibrations of sound.
And now, back to the Jackie Smash Show.
Now, Bill, music and science. Bill? Music and science, science and music. What inspired you to see science in music?
Well, I brought a clip.
Oh, good. Oh, over here, Bill. Right here.
I remember the first time I learned that music was a series of vibrations. When I danced as a kid, I was causing the floor to vibrate, making the air vibrate, causing sound waves, pleasing sound waves. I was a bit older when I realized that I could make vibrations by blowing into a wind instrument. Vibrating my lips set up vibrations in the tube, and I could vary the pitch by opening and closing holes. And in my teen years, I discovered the joys of vibrating strings.
Wow.
Music affects your senses. It can make you sad. It can make a movie scary. Or it can make you happy.
Hey, that's Kenny G.
Music is made of notes, and notes are arranged in groups called measures or bars. So here are 2 whole notes. Each whole note takes up a whole measure. Now, we can divide the measures up into half notes, like this, or quarter notes. See, there are 4 quarters in a dollar, and there are 4 quarter notes in a bar. And we usually call it 4/4 time. 4 quarters. Now, you can keep dividing the music up. For example, there are 2 eighth notes in each quarter note, and there are 4 16ths in a quarter, or 2 16ths in each eighth. And then you can divide a 16th note, and you get 32nd notes when you divide the 16ths up. Or you can have 64th notes, or you can have just 2 eighths on the end of the quarter over there, see, like that. Now, if your musician comes up with something that you like, or then you can write it down. You can record it on the musical notes. See? It's going pretty fast.
Welcome back to Gimme a Tune, where all the tunes are out of tune. Now, gimme a tune. Oh, sorry, time's up. That was Home on the Range. Home on the Range.
That didn't sound like Home on the Range to me.
That's because all the tunes on Gimme a Tune are out of tune. Let's try it again.
I wear my sunglasses at night.
No.
Come on, Eileen.
No.
Oogie, oogie, oogie. Love Shack.
Doesn't quite sound right, does it? That's because it's not quite in tune. The strings aren't vibrating at the right frequency so that they sound good together or good with other instruments. The musician uses a tuning fork that makes the note A vibrates at 440 beats a second. He uses his ear to get one string set up to the note A. Now, to make an instrument like this have a higher pitch, you'd make the string tighter. Make it a lower pitch, you make the string a little looser. Then once he gets the first string set up, he can use that note to make the other strings be in tune. Now, once they're all in tune, not only do they sound good, but they sound good with other instruments in the orchestra or band.
Being in tune is important for music because human ears can hear very small changes in pitch or frequency. You can prove this for yourself. Here's how. Here's how.
Pour some water into 2 identical glasses. Use a spoon to tap each glass and compare the pitches. Add water to lower the pitch of the glass that sounds higher. A little at a time.
Repeat this process until both glasses are in tune, or play the same pitch.
As the frequencies get closer to each other, hearing the differences gets more difficult. But you can still hear, because your ears are very sensitive.
Inside your ear.
Try it.
Now divide in half. Plunk again. You see? It's the same tone, 1 octave higher. Now divide the next section. And the next. Pythagoras discovered the octave had a ratio of 2 to 1. With simple fractions, he got this. And from this harmony in numbers developed the musical scale of today.
By writing music down, we can record it, and other musicians can play it. Now, we write words on a line from left to right. So people came up with the idea to write music on lines from left to right. So we start down here. This turns out to be E. And above that is F. Then G, A, B, C, D, then E again. The top line would be F. See, once it's written this way, we call it musical notation. And then somebody like Chase can play a piece by Bach or Mozart, and those guys aren't exactly around anymore, to hum it for them. See, musical notation is science.
So, Bill, let's talk about rhythm. Now, what the heck does that have to do with anything?
Well, Jackie, music isn't just a pattern of tones and pitches. No, it can be a pattern of beats. That's all, a rhythm.
So what you're saying is that a pattern of beats can affect the sound of music and even work as music itself.
That's exactly right, Jackie. Just as the taps on our feet make a pattern of beats, sticks on a drum make a rhythm too.
We're here with Bill Nye, the Science Guy, and we're talking about science. Well, no, I'm talking about music. Well, no, science. Is there science in music, Bill?
Music is packed with science, Jackie.
So what you're saying is there's science in music.
Oh, yeah.
It's vibrations, sonic sensations that rattle the air in a wave we can ride. A wave of emotion. I've got a notion. It's a journey we take through our eardrums inside.
So just what you're saying, the music I'm playing is making it swaying to my tiny brain.
It's really astounding when the music is pounding. It's all just lovely patterns of sound.
There's science in music, oh yeah. There's science in music, oh yeah.
Vibration vibrations leap through the air.
Can they get into your ear? Every culture has music, and the pattern is clear.
The thumb beating up drums,
The rhythm tuning our breeds,
and blowing, blasting up brass, and twanging, plucking up strings.
there's science in music, oh yeah. There's science in music, oh yeah.
It's just so filled with emotion, these sound waves in motion. Music makes us cry, then makes us laugh, or makes us feel tense, or filled with suspense. By music inflected, our senses are affected.
There's science in music, oh yeah. There's science in music, oh yeah.
Music can affect you emotionally. It can even make you react physically.
Whenever I hear that funky sound, I just gotta throw my body around.
My heart starts thumping, my brain starts to groove, and before I know it, my feet start to move.
There's science in music, oh yeah. There's science in music, oh yeah. There's science in music, oh
Well, that's our show. Thanks for watching. If you'll excuse me, this music is affecting my senses. See ya.
Produced in association with the National
Where'd everybody
Science
go?
Foundation.
Anyway, it's fascinating, really. Music, high sounds over here, low sounds there, mixed together with a rhythm, like that. It's beautiful. Flows. It affects your senses. Sure, it does. Affects my senses anyway. I mean, coming from over there or over there, it just comes into your ears and it's a pattern of vibrations. That's what music is, really. It's a pattern of vibrations. You know, this music is kind of making me think, kind of making me reflect on the show and the science of music, really. I hope it affects everyone that way. I hope everybody watching just thinks about patterns of vibrations, patterns of sound. I'll tell you what it is. Music. Music. It's science!
Again, man makes a projectile of himself, this time from the mouth of a cannon. A man fired in the air. All humankind in action. The universal laws of motion. Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy.
Brought to you by Pushy People. When you need to get something moving, call Pushy People.
Everything in the universe, including you and me, is in motion. Now, forces put things in motion. Forces, like when something is pushed or pulled. To understand motion, you have to figure out if you're pushing on things or things are pushing on you. Whoa. Let me show you what I mean. We are right here. Right here. But we were over there. Over there. Here. After I came through the door, it looked like I was walking through the lab. And in a sense I was. But I was on a platform. And I was standing over pretty much the same part of the main lab the whole time. Till I fell off the platform. You couldn't separate the motions. Now watch them both one more time. Everything in the universe, including you and me, is
in motion. Now, forces put things in motion. Forces, like when something is pushed or pulled. To understand motion, you have to figure out if you're pushing on things or things are pushing on you. Whoa! Take a look at this. This is an air track. When the pump's running, air comes out of these little holes. And it can support the weight of a scooter, like this one. Now, when I place the scooter on the track and let go of it, it just sits there. It doesn't move unless I give it a push. Then it keeps moving unless I give it another push. Or it hits the end of the track. Or maybe another scooter, another scooter, another scooter. Now, here's the thing. If we had enough track and enough air, the scooters would keep scooting forever. There'd be nothing to slow them down.
Well, hardly anything. So when something's at rest or sitting still, it stays sitting still
unless acted on by an outside force. And when something's moving, it keeps moving unless acted on by an outside force. Outside force. Outside force. This is true of everything that you can touch and see. As you may know,
inertia is a property of matter.
Inertia is a property of matter. A bowling ball weighs more than a golf ball. Right now, their weights are supported by these wires. But if I push them or make them run into each other, you can tell that the bigger one is harder to move. We call this property of matter inertia.
Inertia is a property of matter.
This is an anvil. It has a lot of inertia. And right now, it's being acted on by an outside force. Gravity. But it's also being acted on by another outside force. The pull of the chain. Now, to get an idea of just how much inertia it has, we'll lower it.
What's that noise? Whoa! 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 Inertia. Whoa!
Now, just for kicks, this is another type of air bearing. The pump's on here. Now, gravity is still pulling it down, and the air pressure is holding it up. So those forces are in balance, but the anvil has a lot of inertia. And to get it moving, we need a big push.
Oh, no. Not this again. No, come on, Bill, please, no!
What's inertia? I'll show you. Take a playing card and set it over a glass. Set a quarter on top of the playing card. Flip the card hard with your finger like this. The card goes flying, but the quarter falls into the glass. The quarter has inertia. It's not moving, so it stays at rest. The card slides out so easily, it doesn't overcome the quarter's inertia, so the quarter stays put. Of course, once the card's gone, there's nothing left holding up the quarter, so it falls into the glass. Whether something's moving or sitting still, everything's got inertia.
Okay, we got everything packed away. Let's get them to get on the truck.
Here, boxes, boxes, boxes. Here, boxes. Come on.
I think you gotta get tough with them.
Hey, boxes!
Hey!
Get on the truck!
Hey,
little psychology.
Hey, I hear they're giving out free ice cream to the first 20 boxes that get on the truck.
Hey, it says here that nothing gets moved unless they get pushed or pulled.
Great! That means we'll have to do the work, just like last time. Please,
come on.
You're
so heavy. Right on here, just out the door.
Newton's laws of motion. First law, the law of inertia. Things at rest stay at rest.
Hi, Bill. I'm at rest.
Things in motion stay in motion. Unless acted on by an outside force. Second law, to move a mass, you need a force. Here's a mass,
hey,
and here's a force.
It's hard to maintain this position, you know. Thank you.
And then in mathematics, we say force equals mass times acceleration. F equals ma.
So in order to get the same mass accelerating twice as much, you need twice as much force.
Woo! Here's the mass, and here is twice as much force.
Yeah, for sure.
The third law, for every action, there is an equal and opposite reaction. Action, reaction. Equal and opposite, action, reaction.
Here we go again.
Two masses. This one's going to be moving.
Whoa!
Action,
Whoa!
reaction.
Whoa, whoa.
One car moving against two cars. They move off half as fast. That's the equal and opposite reaction. Newton's laws of motion.
What do you think of that?
Life is like a boxcar of inertia.
And now, Newton's laws of motion. Tonight's episode, the first law.
An object at rest remains at rest unless acted upon by an outside force. An object in motion tends to stay in motion unless acted upon by an outside force. Let's watch that again in slow motion.
Without motion, you're just a potato on the couch.
Street luging is a highly modified version of skateboarding or butt boarding.
You get these babies in motion and there's no stopping it.
Let's do it. It's on.
It's on.
We push along the ground to get us started, and then we're under the will of gravity and the percentage grade of the hill to determine our maximum velocity and our speed. What we got here are brakes, our shoes, and our lifeline. Well, that's after one run down about a 50-mile-an-hour hill, so got about 2 or 3 more runs out of those, and I'll have to grab in for a new pair. To have motion takes motion. You either gotta push or pull.
Hey, keep it moving.
Join the Inertia Dance Project for a very special evening of movement and motion. Choreographer Isaac Newton presents his world premiere piece entitled Bodies at Rest, Stay at Rest. Mimes not admitted unless accompanied by a speaking person.
This apple has inertia. It has mass. Right now, the scale is measuring the pull of the Earth's gravity on the apple's mass. Here in the plane, we have a lot of motion. But the scale reads just about the same because the apple still has the same mass. Goes over. Yeah. Now, as we go down, the apple is falling at the same speed as gravity makes it fall. We're weightless. The scale reads 0, but the apple's still the apple. It still has inertia. But now, as we pull up, the scale reads higher because the plane is pulling you, me, and the apple up against the pull of gravity. We measure mass in grams or kilograms. So if I do this, the apple might be weightless, but it wouldn't be massless.
Spacetone News presents the place, space. The question, in zero gravity, do the laws of motion still apply? The answer, yes. Objects in motion in space tend to stay in motion unless something slows them down.
Move. Why won't you move? Go back to where you belong.
Use force.
Huh?
Use force. An object at rest will stay at rest until an outside force acts upon it. Use force, Luke.
Huh. It worked.
So, what'd you learn in school, son?
Nothing.
Son?
Okay. I'll show you. See, we learned that objects at rest stay at rest, unless, of course, they're pushed or pulled. But this cloth, because I jerked it so quickly, couldn't push or pull any of the objects on the table. By the way, nice choice of cereal, Mom.
That's my boy.
Hey, it's lunchtime.
Oh, okay.
Hey, stay right here.
Don't move.
Sure is quiet.
Yep.
Nothing moving for miles around.
No. Pa,
Yep.
there's something I gotta tell you, Pa.
What is it, Delilah?
Well, that last statement you made isn't entirely accurate. Although to you, the observer, it appears that nothing is moving, well, that is merely an artifact of your frame of reference. Like right now, the Earth, it's spinning on its axis at about 1,600 kilometers per hour. And the Earth is moving around that sun about 30 kilometers per second. Plus, our entire solar system here, why, it is just hurtling around the outer edges of the Milky Way galaxy at about 220 kilometers per second. Not to mention the movement of our galaxy within the universe. It's expanding, its speed's approaching the speed of light. That's about 300,000 kilometers per second. So you see, Pa, we're all us here moving pretty fast.
Yeah.
We're all in motion. We're all in motion. Everything in the universe is all in motion. When things are pushed or pulled, they're put in motion. The more the mass, the more force we need. The more inertia, the more force we need. We're all in motion. That's what it seems.
I'm Bill Nye.
Cars go this way while the road's going that way. We're all in motion. We're all in motion. Everything in the universe is all in motion. When things are pushed or pulled, they're put in motion. The more the mass, the more force you need. The more inertia, more force you need. We're all in motion, just like that. That's what it seems.
We're all in motion. We're all in motion.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some third derivative jerk functions to evaluate. See ya!
Oh, I never get used to it.
The dummy is no longer in motion. The dummy is no longer in motion.
Produced in association with the National Science Foundation.
I
love science!
Science!
Yeah. Man, this is a ways down. Okay, here we go.
Science! It's science! 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 Science!